Okay, so welcome along, ladies and gentlemen, to your more than weekly SETI seminar series today. We're very lucky to be joined by Daniel Jontof-Hutter, who's come across to us from University of Maryland. And as you'll be able to tell from his accent, he's originally from Land Down Under. He did a PhD at Monash University in Melbourne, where he was studying dusty rings.
Close. We're getting, yeah.
Yes.
I did undergrad at Monash.
Undergrad,
yeah.
Excuse me, and the PhD at the University of Maryland. So we'll make sure that we get that right. He is going to be working with Jack Lissauer at NASA Ames on a NASA postdoc program starting from July. So if you'll join me in welcoming Danielle.
Thank you all very much for having me and coming to my talk. So I haven't quite got a PhD yet. I'm defending my thesis in 2 months, and then I'm going to be starting my first postdoc here in California, where so far it seems colder than in Maryland. I was a little bit surprised. So I'm going to be talking about the dynamics in the dusty rings of the giant planets, and we're going to be looking at magnetic field effects on orbiting dust grains. A lot of what I'm going to be doing is just basic or fundamental dynamics, just how grains move with the electromagnetic force and gravity acting on dust grains. And then we're going to use that to solve a real problem at the Jupiter system. So there's going to be a lot of fundamental dynamics, but bear with me and tell me to slow down if I talk too fast or if there's anything that's not clear. And let's make the most of it. So when are electromagnetic effects important? Well, the most high-profile problem in these sort of dynamics are the spokes in Saturn's B ring. When the Voyagers flew past Saturn in the early 80s, they found these radial markings, these dark patches on a light background as they flew past Saturn. And we know that magnetic field effects are very important because the edges of these radial spokes, I don't know who coined the term spokes, but to me they're splotches. The radial edge is co-rotating with Saturn instead of just orbiting at the Kepler speed like a ring particle. So we know that somehow the magnetic field is responsible for this, and there are a few theories out there. They've all got their strengths and weaknesses, but at the end of the day, we don't really understand what's happening in this movie. So that's one of the mysteries that still remains from the Voyager era, which motivates the dynamics that I'm studying. Another example are the Lorentz resonances. So if you have a dust grain that is orbiting in a rotating magnetic field, then if its orbital frequency is an integer ratio with one of the spatial periodicities in the rotating magnetic field, you can get a destabilizing Lorentz resonance, where if you have any non-axisymmetric magnetic field terms, if you have, for example, in this image, like a tilted component in Jupiter's magnetic field, this is Jupiter's spin axis, and that's the magnetic dipole axis. A grain that's orbiting in this environment is constantly having, flip-flop in magnetic field, in the magnetic force that it experiences. So that will cause a resonant destabilizing effect. And this explains the actual structure of the main ring at Jupiter. Burns et al. and Burns, Showalter, Les Schaefer, and others in the early 80s, they realized that dust grains that start off in Jupiter's main ring, this is an optical image, this is the infrared, grains that are released in the main ring from the tiny satellites there, as they spiral in with Poynting Robertson drag, radiation effects, they slowly spiral in, and when they hit this 2-1 resonance between their orbital frequency and the spin frequency of the planet, they're going to get these resonant kicks from the magnetic field, and that puffs them up to form this halo, this dust that's seen above and below the ring plane, because they get excited inclinations, they get excited vertical motions. So that's an example of where the magnetic field of Jupiter is actually sculpting the shape of the ring as we see it. So the third example of where magnetic field effects are important, and this is the one I'm going to be focusing on the most today, are the high-speed dust streams. So Ulysses is a spacecraft that flew by Jupiter in 1992 to get into a polar orbit around the Sun. And when it did so, it discovered a stream of high-speed particles up to 200 kilometers a second coming from the Jupiter system. The dust grains are very, very small in the dust stream, 5 to 15 nanometers in size. And so we're going to figure out exactly where these dust grains are coming from and how. So, firstly, when is the E&M effect important? Well, a dust grain has to pick up an electric charge in order to be affected by the magnetic field. So how does a dust grain do that? Well, just being in the plasma environment, a dust grain is likely to pick up a net negative electric charge. And the reason for that is that in the plasma, the electrons collide with the dust grain and are absorbed more frequently than the slower, heavier ions and protons. So it's going to end up with a net negative electric potential. And on the other hand, the effect of sunlight ejecting photoelectrons from the surface of a dust grain would cause a net positive charge because the grain is losing electrons from sunlight. So these two processes, amongst others, compete, and a typical electric potential on the dust grain in either Saturn's dusty rings or Jupiter's dusty rings could be anywhere from -20 to +10 volts. So you have a grain with this electric potential and it's moving through a magnetic field, therefore you have the Lorentz force, the E&M force. So this is the equation for the Lorentz force. I'm going to introduce a little bit of notation. So the force is due to a charge Q moving at a speed v through a magnetic field B, and this component of the force is just due to the rotation of the magnetic field itself as the planet spins. And if we take this component of the force and divide it by the strength of gravity acting on that dust grain from Jupiter, we get this parameter which we call L, and it's our analog for the charge to mass ratio, how important the E&M force is compared to gravity. So if this L number is much, much greater than 1, we're in the EM regime or the Lorentz regime where the magnetic force is much more important than gravity on that dust grain. If L is much less than 1, close to 0, then gravity will determine how that dust grain will move. It'll move like a ring particle. And if L equals 1, or plus or minus 1, it could have a sign, then for that dust grain, the magnetic field, the magnetic force and gravity are both comparable. They're both important. So this is for an aligned dipole magnetic field where we're assuming that the magnetic dipole is aligned with the spin axis of the planet. And we're going to test that assumption later. But so we have this very ugly equation, which is the potential for a dust grain that is orbiting in a centered and aligned rotating magnetic field with gravity. So it's a big mess, and this is unfortunately the simplest configuration we can get. If we had the magnetic field tilted or offset, or if we included other components of the magnetic field, we would not be able to write the equation on one slide. So we have this Hamiltonian, this potential, and we want to know where is this reasonable, where can we get away with using this aligned magnetic dipole approximation, because if we can use that assumption, there are a lot of problems that we can solve just with algebra without even doing computer simulations. So for example, this is the radial distance and the cylindrical distance. If the ring plane and the magnetic equator are in the same location, well, then you can have this rho equal to r, and you can get a lot of cancellation, and you can start solving for some of the dynamical problems, how these dust grains will move. So is this a reasonable assumption? Can we just assume that the magnetic fields are like this? Well, here are the magnetic fields of the outer solar system. I'll point to this one now. Neptune, its spin axis is that way. Its magnetic dipole axis is 47 degrees off that, hopelessly misaligned. That's a very poor example of where you might use an aligned dipole approximation. And similarly, Uranus It's the planet's spin axis and its dipole axis are completely misaligned. The dynamics there is not easy to solve analytically. It's something that you'd have to use computer simulations to figure out. But look here at Saturn, Jupiter, and the Earth. Saturn's magnetic dipole is actually perfectly aligned with the spin axis of the planet. Cassini at Saturn has managed to narrow this down to just 6/100ths of a degree. As far as we can tell, it's perfectly aligned with the spin axis of the planet. The magnetic field is a little bit offset from the center of the planet by a few thousand kilometers, but this is the best example of where you could use an aligned dipole approximation. And Jupiter and the Earth are both reasonably well modeled by a planet with a moderate tilt of 10 or 12 degrees. So Jupiter, which we're focusing on, has got a tilt of 10 degrees. We're going to see if we can get away with an aligned dipole approximation for Jupiter because that tilt is so small. So, as I said, I'm going to give you some fundamental dynamics. So bear with me and ask me questions if need be, and then we're going to solve a real problem. So we're going to look at, firstly, the smallest dust grains that are completely dominated by the magnetic field. How do they move? Well, over the shortest time scale, they're going to exhibit gyromotion where they rapidly spiral around magnetic field lines. And over a longer time scale, a dust grain might drift up a field line to a region of higher magnetic field strength, and then there is actually a restoring force back to the magnetic equator. So you can confine a charge in a magnetic bottle. So this is called mirror motion. It's a slower motion parallel to magnetic field lines because the magnetic force itself is always at right angles to the motion. So this is a slow component which keeps the dust grain tied vertically to the magnetic equator, and a typical time scale for these vertical oscillations, or this mirror motion, is say 10 hours at Jupiter. And grains smaller than about 10 nanometers in size are in this EM-dominated regime, this Lorentz regime, and exhibit this motion. So let's look at an example. So I'm going to show you some simple simulations. I have here 3 dust grains. I'm losing the laser. Okay, 3 dust grains here. And they all have a charge to mass parameter. The ratio of the Lorentz force to gravity for them is -3. So they're reasonably well dominated by the electromagnetic force. And this is the side-on view, and this is the view from the north of the same 3 dust grains. I'm going to release them from Jupiter on Kepler orbits as if they've just been released from the small moons near Jupiter. And we're going to look for their vertical motion or their mirror motion after we release them. So this is what happens. These outer 2 dust grains are exhibiting stable mirror motion where they bounce between these points north and south of the equator. I've given these grains a small initial latitude just so we can see their vertical motion. But what's happening here, the dust grain closest to the planet, instead of being attracted to the magnetic equator, it's vertically unstable. It's being repelled from the magnetic equator, and it's just climbing up a magnetic field line and crashing into the planet at high latitude. So what's happening there? This is not really easily explained in the prior understanding of how you should have stable mirror motion about the equator, because the equator should be the energy minimum that attracts the dust grain. So the first to realize that this actually happens, this is actually what would happen, were Northrop and Hill in 1982. They realized that you can't ignore the fact that the planet is rotating, and you can't ignore gravity, even though these are very small dust grains. And if you put an assumption that the force of gravity, the centrifugal force on a dust grain, so the force outwards as the magnetic field is spinning, and the Lorentz force, if you make them all sum to 0, you'd have the grain orbiting on a perfect slow circle around the planet. And if you put that equation for that into the Hamiltonian, that big messy equation I showed at the start, you get this, you get the algebra, you get to prove that these grains are actually vertically unstable, and they'll climb up the field lines and crash into the planet if they're launched within the certain critical distance. And Northrop and Hill were studying this distance at Saturn, but it's exactly the same here at Jupiter. The distance would be 1.95 Jupiter radii. But in coming up with this model, Northrop and Hill ignored the gyro motion, the rapid gyrations around the magnetic field line that we know dust grains will have, because they're launched at the Kepler orbital speed. They're launched at a different speed to the rotating magnetic field, so they must have, some rapid spiraling around the local magnetic field lines. They're not launched at this special speed which helped Northrop and Hill solve that equation. So they explained this vertical instability, but they did have an approximation which ignored the gyro motion, and we're going to test their model. Yeah.
Is this distance related simply to synchronous distance or no?
Yes, it is. So it's the cube root of 2/3 of synchronous orbit, and it's a very simple. You get this analytical solution. It's a single number. Yeah. So this is a stability map. We want to know which dust grain orbits are unstable for all charge to mass ratios, for the largest ones like rocks and the smallest ones down to ions, and for all distances from Jupiter, because we just saw that vertical instability depends on how far you are from Jupiter. We want to know at which distances these dynamical instabilities are important. So I've made here a stability map where I've got individual dust grain trajectories for a whole range of charge to mass ratios. The largest ones here on the right are in the Kepler regime, and the smallest ones in the left are in the EM regime, or the Lorentz regime. And I'm launching all of these individual dust grains between Jupiter's surface at 1 Jupiter radius out to 3 Jupiter radii. And as Martja said, the important distance we're talking about here is the synchronous orbital distance. And the reason for that is that if you're launched at the Kepler orbital speed, at that distance, you're not moving relative to the magnetic field line. You're not going to experience the Lorentz force at all. So that is the important distance scale. So I've made my simulations out to 3 Jupiter radii just to include that distance so we can see what happens on both sides of that boundary. So the white space are all dust grain orbits that were perfectly stable and continued indefinitely. The dark gray are grains that were vertically unstable. They climbed up the magnetic field lines and crashed into the planet at high latitude, just as Northrop and Hill predicted. And this lighter gray here is a little bit more complicated. They're grains that were unstable in the magnetic equator, but instead of crashing into the planet, there was some high latitude restoring force which saved them. So they're globally stable, and they do remain orbiting indefinitely, but they're always repelled from the equatorial plane. So they do some funny business, but they survive. So this is the Northrop boundary, this curve here, the dotted curve. And in the Northrop equations, every grain launched within that distance should be unstable and should crash into the planet. And we see this region of stability inside the boundary here, which doesn't match their solution. And a whole new region of stability close to the planet, which is precluded from their equations. So their model doesn't match the data. We know why it doesn't match the data. They didn't include that mirror force, that stabilizing mirror force that we know dust grains must have if they have any gyro motion at all, which they do. So I'm not going to put too much time into equations here, but basically this is the expression for Northrop's model, and it assumed that dust grains are on perfect orbits without any gyro motion. And we wanted to extend that to include other effects that are stabilizing. The first one is the mirror force, which we know will stabilize the orbits and keep dust grains attracted a little bit more to the magnetic equator. And we also found there are other effects. If you average the force of gravity and the centrifugal force around a gyro loop, if you integrate around that gyro loop, you get some extra you get a solution that has got some extra terms that is slightly more stable than Northrop's equation. So this is our expression for the bounce frequency, how often dust grains will bounce up and down with these extra effects. So let's test our model against the data. This is the bounce period in hours for vertical motion at Jupiter for an electromagnetically dominated grain. So this L parameter is minus 10,000. The magnetic force is 10,000 times as strong as gravity on this dust grain, on these dust grains. And so I have a whole range of launch distances here from 1 to 3 Jupiter radii. And the synchronous orbit was at 2.25 Jupiter radii. So the red points are numerical data. So I've used a computer to simulate the actual trajectories and measure how long it takes for them to bounce up and down. And the blue curve is the solution. It's that equation that I just showed you in the previous slide. So it's matching the data very nicely. The green curve is the Northrop solution. And there are two things that are worth saying here. Northrop is absolutely correct at synchronous orbit, but everywhere else, the Northrop equation has got bounce periods that are too high because they underestimate the stability of the orbit. They have grains that are slightly more willing to leave the equator and crash into the planet than what actually is the case. So everything within 1.95 Jupiter radii is unstable in Northrop's equations, but we find, and the data confirms, this region of stability closer to the planet.
What are those data again? Where did you get those data from?
These data are numerical simulations, so with a code that can integrate the actual trajectories and see what happens. So this is the stability map again, and these black curves are my model boundaries for where, using my equation, where the transition between unstable and stable would be for all distances and charge to mass ratios. So again, my model is working perfectly well in the Lorentz limit. It loses a little bit of accuracy as we get to larger dust grains further to the right, and there are other higher order effects that we've ignored. For example, we assume that the gyrocycles are perfect circles, but they end up becoming elliptical, and there are some other higher order effects that we neglect. So our boundary loses a little bit of accuracy, but it's still an improvement on the Northrop boundary, and it allows for this other solution closer to the planet. Just another point to show with our new bounce frequency. These points here behind the curve, and I'm not getting any laser. Oh, there we go. It was my finger in the way. These points here are dust grains that have got excited vertical motions following large radial excursions. So there is this sloshing between their radial and their vertical motion. In planetary dynamics, there's a similar mechanism called the Kozai mechanism, where eccentricities and inclinations can exchange energy, or the orbit can switch between having a high eccentricity or high inclination over time. There is a similar effect that we're seeing here with these dust grains. So this curve here, which is explaining where these high latitude oscillations are arising, is at the resonance between the radial frequency, and Mendes et al. In 1982 came up with this equation for what the radial frequency should be with both forces, and the bounce frequency, which I'm showing you today. This 2:1 resonance picks out those data quite nicely. So this is the negatively charged dust grains in an aligned dipole magnetic field. And we're nearly there. There's a little bit more dynamics we've got to do before we're going to solve a problem. We want to know, we've looked at the vertical motion. Now we're going to look at the radial motion of the dust grains. This is the radial range of negatively charged dust grains in an aligned dipole magnetic field. So we have here a whole bunch of charge to mass ratios, with the smallest ones on the left in the EM regime, the Lorentz regime, and the largest dust grains that are Kepler dominated or gravity dominated on the right. We're launching all of them at the same location at 2.5 Jupiter radii. That's near Amalthea in Jupiter's Gossamer ring. And we're looking at their radial range of motion, just how far these grains move, their furthest distance and the closest distance to Jupiter that they experience in their orbits. So the largest dust grains in the gravity-dominated regime, they're on low eccentricity ellipses, just like ring particles or satellites. So they've got a very small radial range of motion. And the smallest particles on the left side, these are EM-dominated. They're spiraling rapidly around their local magnetic field lines. So they too have a small radial range of motion. But between these two regimes, where E&M and gravity are comparable, these dust grains are having a huge radial excursions, roughly halfway from their launch distance to synchronous orbit, which is down here, and that is tens of thousands of kilometers. But these grains, although they have large excursions, their orbits are perfectly stable, and they're always confined between their launch location and the synchronous orbital distance. And that's true for all negatively charged dust grains in an aligned dipole magnetic field. I should just mention that the points here are numerical data from simulations that I ran, and the curve is an epicyclic model, an equation using that Hamiltonian that solves for this from Schaefer and Burns in 1994, and their approximation works very well. It explains the data quite nicely. So that's the negatively charged dust grains. The positively charged dust grains can be radially unstable. So looking at exactly the same dust grains launched from 2.5 Jupiter radii, we're looking at their radial range of motion over all charge to mass ratios. And I'll show it on this side now. So the largest ones, again, are on low eccentricity ellipses, a small radial range of motion. And the smallest ones, again, are tightly bound to their local magnetic field lines. And between these two regimes, where E&M and gravity are both important, these grains escape. They don't just escape, they're actually expelled at high speed. So these would be contributing to the high-speed dust streams from Jupiter. If I'd launched them inside the synchronous orbital distance, like below this location, they would be radially unstable and crash into Jupiter. You don't ever see grains crossing that synchronous orbital distance. It's a robust boundary in the dynamics. So this is what the stability map looks like. Which grain orbits are unstable for all charge to mass ratios and all launch distances from 1 to 3 Jupiter radii for the positively charged dust grains in an aligned dipole magnetic field. And we're going to try and explain the boundaries between stable and unstable orbits. We want to be able to solve for when a particular dust grain launched in Jupiter's rings is going to survive or not. So we're going to start off by looking at the vertical instability. And I showed you my solution earlier for the negative grains. Here it is for the positive grains. Again, it works perfectly well in the Lorentz limit in the EM regime, but our model loses a little bit of accuracy as L declines and gets closer to 1. Basically, as the dust grain, their radial excursions become very, very large and unwieldy, you can't, all of the assumptions that went into our equations are harder to justify. So our model is going to lose accuracy. The epicyclic model itself fails. So it makes it a little bit harder to explain all these radial instability boundaries because we can't use the epicyclic model. Just showing you for these outer stability boundaries, Horani in 1993, he tried just that simple epicyclic model, like when dust grains are likely to have large radial excursions, large enough to escape, if that could explain this boundary. And he was applying the model further out from Jupiter, and it worked pretty well out there. But if you get closer to synchronous orbit, it doesn't work well enough. This boundary on the right is from Hamilton and Burns 1993. They used an energy argument. They looked at that equation for the Hamiltonian, the energy, the potential that I showed you at the start, and they found the solution that if L is less than 1/2, the charge to mass ratio parameter, if L is less than 1/2, the dust grain is bound, and if L is greater than 1/2, it has enough energy to escape. Yeah, Matya.
So, when you talk about radial motion, how does it look like? Are you crossing magnetic field lines?
Oh, yeah, at high speed. They're accelerating, yeah.
Okay, so is it, if you start on the equator, the radial motion combined going on the plane, or is it all in the plane?
It's in the plane. If you tilt the magnetic field, you don't see any difference with these boundaries. Yeah, it's straight out radial. So that L equals 1/2 solution is something similar arises in debris disks. I don't know if anyone here is familiar with circumstellar debris disks. There are like dust around other stars. In that environment, you have dust grains that are bound to the star by gravity, but they also experience radiation pressure where the starlight is pushing on them, trying to push them outwards. And there's a solution that if the ratio of the radiation pressure from the star over the gravity of the star is 1/2, then they're just on that threshold. And if it's greater than 1/2, they're blown out from the star. And if it's less than 1/2, they continue orbiting the star. So it's the same solution that you would get in a debris disk, in dusty disks around other stars. And we're seeing the same thing happening here. So using this energy argument, we're going to try something. We're going to use the energy to try and solve for these other boundaries when dust grains are likely to escape, and inside synchronous orbit when they're just on the threshold of crashing into the planet. So with a lot of algebra, you can eventually get these boundaries and understand what's going on when a dust grain is likely to be unstable. So congratulations. Yeah, thank you very much for bearing with me. We're done with all the fundamental dynamics, and now we're going to use this to solve a real problem. Where does the high-speed dust stream come from? And there are two camps in the community which advocate these two different possible sources for the high-speed dust stream. The first possibility is that they could be coming from the Gossamer rings, which is dust from Phoebe or Amalthea, tiny moons that orbit interior to Io. We know that the dust streams can't be coming from Jupiter's main ring, which is inside synchronous orbit, because no dust grains ever get to cross synchronous orbit. So Gossamer rings is one possibility. And the other possibility is Io's volcanoes, dust from Io's volcanoes. If it can get away from Io's gravity, if it's positively charged, it'll join the high-speed dust stream. So these two camps don't agree with each other where the dust comes from. I think we're ready to resolve the debate. I don't know if the Gossamer rings people are willing to concede, but I think Io is the more likely source of the high-speed dust stream. And I'm going to give you three reasons. None of them on their own are strong enough, but the three of them add up to a compelling case for Io. The first one, it comes from Galileo data. Galileo orbited Jupiter for 6 years, and it was constantly measuring these high-speed dust impacts on its detector, and measured the rate at the impact. So the rate at which dust was hitting the detector varies a lot. And if you look at all the frequencies at which dust is hitting the detector, Io's orbital frequency relative to the rotating magnetic field ends up being one of the important components. So that's evidence in the dust stream rate that Io's orbit is modulating or is very important in the source of the dust. The second line of evidence comes from Cassini's Jupiter flyby in 2000 when it was on its way to Saturn. Cassini's cosmic dust analyzer can actually measure the composition of dust grains. So they found that the dust grains are rich in sodium and sulfur, which is consistent with Io's volcanoes. So there's another line of evidence for Io. And the third line of evidence is a dynamical argument using what I've been talking about today. So this is, I showed you the stability map for positively charged dust grains from 1 to 3 Jupiter radii earlier. Now if I extend it out to 6 or 7 Jupiter radii, Io is out here at 6 Jupiter radii. So these 10 nanometer sized dust grains, if they're launched, if these dust grains are coming from Phoebe and Amalthea, between 2.5 and 3.5 Jupiter radii, those are dynamically stable, they're trapped. But exactly the same dust grains launched out at Io would be radially unstable. They would be expelled at high speed because they're on the unstable side of this boundary between the stability boundary. So that's another dynamical argument which favors Io just because we know that the dust grains are really, really small in the high-speed dust stream. So we have a problem because the dust streams are coming from Io, or the Io plasma torus. There is this region of plasma, of charged gas, which orbits at Io's distance. It's about 2 Jupiter radii thick. And dust grains that are in that environment are likely to be strongly negatively charged. But we know that in order to have these grains expelled at high speed, they have to be positively charged dust grains. So how are these dust grains, which are probably trapped in the Io plasma torus, going to escape? How are they going to get out into an environment where there is less dense plasma? Because remember, the plasma causes a negative charge. If they get out of this plasma torus to a little bit further out from Jupiter, well then the effect of sunlight in the low-density plasma environment can make them positively charged and they can escape as high-speed dust streams. But first we have to explain how they escape from this plasma torus. So yeah, as I said, the negatively charged dust grains are radially stable. They're always confined between their launch distance and synchronous orbit. And they cannot escape, so how are we going to form the high-speed dust stream? Well, up till now, we've assumed Jupiter has an aligned dipole magnetic field, aligned with its rotation axis. Its full magnetic field is well modeled with, as I showed earlier, a small tilt of about 10 degrees. So let's see what happens if we go to Jupiter's actual magnetic field and if that can help us have the dust grains escape. You've seen this plot before, again, just from 1 to 3 Jupiter radii. This is the aligned dipole magnetic field showing where the instabilities arise for negatively charged dust grains. And for these negatively charged dust grains, the only instability is this one inside synchronous orbit. And out here near Io at 6 Jupiter radii, everything is stable. So that's the aligned dipole magnetic field. Let's tilt Jupiter's magnetic field and see what happens. So we get all this stuff. The blue dots are showing dust grain trajectories that had excited radial motions away from synchronous orbit, something that cannot happen for a negatively charged dust grain in an aligned dipole field. So the solutions that we showed earlier cannot explain this because with Jupiter's tilted magnetic field, these dust grains are moving outwards instead of just moving towards synchronous orbit. And the red ones are dust grains that escape Jupiter entirely. We don't have to have them escaping entirely to explain the dust stream. We just have to have them escape from the Io plasma torus, and then they can become positively charged in a low-density plasma environment, and they'll feed the dust streams. But so this red stuff is overkill. We don't have to have grains escaping. We just have to have them move out radially. So we can see in the data that these grains are moving out radially. It would also be nice to understand why they're doing it. So what I'm showing here is the energy of the dust grain's orbit using that messy Hamiltonian that I showed at the start, the total energy of the dust grain's orbit. At the top, I'm just showing you for this negatively charged dust grain, its radial motion. So I launch it at Io at 6 Jupiter radii, and it has these radial oscillations that are perfectly stable. It does this indefinitely because it's an aligned dipole magnetic field. And I've given this dust grain a tiny initial latitude of 1/100th of a degree, just so we can see that its vertical oscillations are also very stable. And this is the total energy of its orbit. It's perfectly conserved because we have this Hamiltonian that works, and it explains exactly how the dust grains move to within 1 part in 10 to the 15, which is the numerical error in the code. This equals -1. So the dust grain, so the ratio of, so there's no change in energy as this dust grain is moving because we're in an aligned dipole. So that's good. I mean, there's nothing surprising in here, but it's good to have a reality check on our simulations. If we go to a tilted dipole model, so this dust grain launched at 6 Jupiter radii, it's now having these stochastic kicks in radial distance where it can be pushed out to greater distances and closer distances from Jupiter. And it eventually climbs out higher and further away from the planet. Looking at its latitudinal motion, you can imagine that a dust grain that has got huge radial excursions of many Jupiter radii across the magnetic field lines, in a tilted magnetic field, that's going to have a strong signal in latitude as well. So this is stable vertically, but it does have a large amplitude. And here if we look at the Hamiltonian, so we don't have, remember we don't have an equation to describe the energy in a tilted dipole. We're looking at the effect of the tilted dipole on the energy for an aligned dipole magnetic field, just to show the effect of the tilt on this dust grain's orbital energy. And it's climbing, it's getting these stochastic kicks in energy up and down. It's a random walk. And for this dust grain, synchronous orbit is a boundary it can never cross. That's very robust. But there's nothing stopping the dust grain from eventually escaping if it's going on a random walk. So for that reason, its fate is sealed. It'll eventually escape the planet. But again, this is overkill. I don't actually have, this grain doesn't reach positive energy or the escape speed just yet at the end of the simulation, but I don't have to do that. I just have to have it escape out to 7 Jupiter radii to escape that plasma torus. So again, this is another example of overkill. So what is causing these stochastic kicks in energy? Well, we want to explain the structure, like why is this instability, why is some of these grains escaping or have excited radial motions and others don't? There's a lot of white space there as well, so we want to be able to explain exactly which grains are going to suffer these radial excitations. So that's a tilted dipole magnetic field. If we go to Jupiter's full magnetic field, and we include all the components of the magnetic field as measured by the space probe, the Pioneer space probes that were the first to get there, and measure it, then you get a whole bunch of grains that are escaping, and more of these fingers of instability that are pointing to the right. Just as an aside, we see here that within synchronous orbit, going to Jupiter's full magnetic field has destabilized all the grains inside synchronous orbit in the Lorentz regime, in the EM limit. So before we just had that instability which was confined between my solutions for the aligned dipole. Here we see that everything out to synchronous orbit is unstable. Well, whatever plasma exists at Jupiter within that distance that is generated by collisions between dust grains or with the moons, whatever cold plasma is generated at that location is unstable. So this is, in a way, a prediction for what sort of plasma environment the Juno spacecraft will be immersed in when it enters Jupiter's orbit in 2016. So getting back to the escaping dust grains, all of these fingers instability are pointing to integer ratios of the Kepler orbital frequency, that's the n, and this is the spin frequency of the planet. So at this distance here, this outer one, the planet's spin rate is 3 times as fast as the Kepler orbital frequency. So it's getting, it's in the resonant location. So what we have in fact identified are Lorentz resonances for higher charge to mass ratios. So I mentioned the Lorentz resonances at the start. These can explain the structure of the main ring. So this is the main ring at Jupiter. This is inside synchronous orbit, and dust grains that are released or formed in the main ring, as they pass the 3-2 inner boundary, they pass one resonance and have extended radial motions. But when they cross the 2-1 inner boundary, they have excited vertical motions, and this explains the halo that we see in infrared light at Jupiter's main ring. But the people who've looked at the Lorentz resonances have only considered them in the Kepler regime for very large dust grains where the magnetic field is a weak perturbation. It's a weak force that can destabilize dust grains and excite their inclinations. But for them, the only important frequency, or the ratio of frequencies, was the Kepler orbital frequency of the dust grains and the spin of the planet, or the spin of the magnetic field. And we've found, and these are the equations that model it, that the orbital frequency of the dust grain depends on the charge to mass ratio. So we have here azimuthal motion, the radial frequency, and the vertical motion. We have these 3 equations that model the different frequencies at which these dust grains are moving. So the first one, hats off to Northrop and Hill in 1982, and Mendes et al. I gave them credit earlier for the radial frequency. And this is the bounce vertical motion model, which I've shown you today. If we use these frequencies on dust grains, we see that they are not the same as the Kepler frequency for higher charge to mass ratios. So what do I mean by that? I've got a whole bunch of dust grains that I'm launching at 2.5 Jupiter radii. And so here are some grain sizes along the top axis and some charge to mass ratio parameters on the bottom axis. So on the right side, all these 3 periods are exactly the same. They're just the Kepler orbital period. And if you go to higher charge to mass ratios, or you move to the left, then the radial period, the vertical period, and the azimuthal period, they all diverge. They all have their own frequencies. So the resonances between these frequencies will be at different locations because the spin of the magnetic field is constant, and these frequencies are at different locations. So if we find where those locations should be, based on these different frequencies, we get these solutions, these black curves, which track these instabilities quite nicely. We've done something here that is a little bit, it's cheating a little bit, because those equations are really only valid in an aligned dipole magnetic field, and we're using them to solve for the Lorentz resonances, which you can't have Lorentz resonances in a aligned dipole magnetic field. But because Jupiter's magnetic field has got that moderate tilt, we're getting away with it. So this is an example of getting away with an aligned dipole approximation to solve another problem. And we see here these Lorentz resonances, they increase in strength as the magnetic force on a dust grain increases. So they all get wider, they overlap, and they destabilize all these dust grains. And these ones here out at Io, these small dust grains out at Io, they're destabilized very quickly. They escape in as little as a few days. So that would provide a mechanism for them to get out of the plasma torus. So that's the resonances with radial motion. Because the radial motion and the vertical motion have got different frequencies, the curves for the vertical Lorentz resonances are at slightly different locations. I'll actually toggle between that so you can see the shift. Slightly different. It's most dramatic inside synchronous orbit here. You can see that's the radial stability, but that's the vertical stability boundary we derived earlier, and it merges with these Lorentz resonances. It's radial, it's vertical, and they explain different features on this map, which dust grain orbits are unstable. So just for completeness, I'm going to show you the effect of these Lorentz resonances for positively charged dust grains in Jupiter's full magnetic field. These black curves are the radial stability boundaries in an aligned dipole magnetic field, and having Jupiter's full magnetic field, not surprisingly, causes more dust grains to be unstable, but we can explain where and why they're unstable using these Lorentz resonances. These are the radial resonances, and there is this exact solution on the synchronous orbital distance, which is 2 minus root 3. All the solutions converge onto that one number. And we get a similar set of curves for the vertical stability boundary, the vertical Lorentz resonances. So there I'm going to conclude. We have these analytical solutions where we can try and understand which dust grain orbits are likely to be unstable just from their charge to mass ratio and their launch distance from Jupiter. And using the epicyclic model, that we derived all these solutions using an aligned dipole approximation, but even where you don't have an aligned dipole magnetic field, it's helping us find those Lorentz resonances for all charge to mass ratios. We've extended them to smaller dust grains at higher charge to mass ratios, and we've found that negatively charged dust grains can escape from Jupiter if you have all the higher order magnetic field terms, and therefore Io's plasma torus can feed the dust streams. And are there any questions?
Daniel, if I can start with the first question. So can you make predictions about what size distributions the grains should have being ejected as well from your models there, and can these be tested?
I wouldn't make a prediction for a size distribution in general, but I would, if you could find that L equals a half boundary, which is very robust, there would be a cutoff. There would be grains larger than that, but not grains smaller than that at that part of your size distribution. There are other effects which expand these stability boundaries, which I've ignored, and I can ignore them in this problem, but I haven't really justified that. But if you have the charge on a dust grain varying with time, so its charge to mass ratio can change from L equals a half to L equals a quarter and so on, then you get more destabilizing effects, and if you account for that, you might be able to make a prediction for what size grains are going to live and which ones are not going to last, and you would be able to find that. It's actually something I'm working on. I've been working on since I've worked on this problem.
Okay,
yeah.
And extending to Saturn, what obstacles stand in your way from just saying, oh, well, it all works exactly the same in Saturn?
Well, Saturn's not going to have any Lorentz resonances, and Saturn also has a high-speed dust stream that Cassini has discovered. They don't have any Lorentz resonances because the magnetic field is axisymmetric. So there's no, as a dust grain orbits Saturn, there's no change in magnetic field strength along its path. So the source of the dust streams at Saturn is still an open question. It's something worth looking at. You want to know what the different plasma environments are at different distances from Saturn, probably in the E-ring near Enceladus. But Saturn is, the origin of the dust stream at Saturn is a question worth addressing. But the biggest problem at Saturn that motivates me is the spokes in Saturn's B-ring, and that's something I'm working on. Yeah.
I was going to mention that. Do we have any other questions? Yeah. Okay, I'll mention it, then we'll go. All right. So we had Larry Esposito a couple of weeks ago. He said that there was a paper by Carl Mitchell that came out that says that the spokes were due to a plasma effect in the rings. Do you want to talk about that?
I'll go back to the spokes and we can look at the movie while I'm talking about it.
Because I just know that Lawrence Doyle is going to, when he watches this video, he's going to be
So
excited about this.
they realized straight away in 1981 that there were magnetic field effects here, and there were a couple of theories that came out in the early 80s. The most popular theory was that after there is a meteoroid that collides with a particle in the B ring, it puffs up a lot of dust and plasma, and as the plasma is going to move out radially, and as it does, it's going to give dust grains on ring particles enough of an electrostatic force to boost them out of the ring plane, lift them out of the ring plane. And it's described as the dust, and as this cloud of plasma moves out radially, as the cloud progresses, more dust grains are moved up radially. So it depends very, very much, for their model, it depends very, very much on exactly what's happening in the ring plane, in the B ring, what sort of potentials you need to lift dust off the ring particles. One of the problems with that theory was the time scale. For this radial plasma, this plasma to move out radially and form spokes, it has to move faster than what we're seeing. It has to move. The spokes form in a very rapid time scale, and so a moving plasma has to be able to move at that speed, and that has not worked out so well. I'm still waiting to see the Cassini data, and Colin Mitchell is actually the one who's studying the spokes for Cassini. So see what they found. But from the Voyager data, it doesn't explain everything, that model. But the charging environment in the B ring is crucial to any model for the spokes. So,
yeah, you indicate that there's a difference in what happens to the positively charged particles versus the negatively charged particles. Isn't that only going to lead to a disparity in charge within the plasma, and does the coolant force start to become important at that point?
That's a very important thing that I've ignored. So if dust grains are escaping, we have to assume that they're carrying negative charges with them. So we assume anyway that a dust grain is surrounded by charges of the opposite sign as a Debye sheath. Like a Debye sphere is just a bunch of charge with a dust grain at the middle. So if the dust grain is being expelled radially, it's going to take its opposite charges with it. Otherwise, if it wasn't doing that, and this is not something that I study in detail, then if you're losing positively charged dust grains, you are eventually going to have an environment where electrons would like to leave as well. So they would have to. It would be energetically favorable for them to leave as well if they could. So, yeah, it's a good question.
Right here. Did any of our probes have the ability to measure charges on particles out there? And if so, to what extent has that data added confidence to your simulations?
I think Cassini, they are able to measure the electric potential on dust grains. But we don't really know exactly what, for my approximations, in all my models, I've shown you what sort of size dust grains we're talking about. We don't really know if these are, so here for example, I say these are the grain sizes and this is the charge to mass ratio. We don't really know these grain sizes. I've just assumed, oh, well, let's make it -5 volts and a perfectly spherical grain of density of 1 gram per cubic centimeter. And so we need the people who observe dust grains and people who do lab experiments on dust grains to tell us what's reasonable, like what the densities are and what the shapes are of the dust grains. But until then, I use this as my independent variable just because it doesn't make any assumptions.
I have a question about one of the early formulas. There were just more variables there than I could keep track of.
Yeah,
there was
sorry.
a little g, and there was a little g with a 10 or an IO as a subscript.
Sorry, I should have explained this. So this component here is called the co-rotating electric field, because it moves dust grains radially across magnetic field lines. And if we take this component of the E&M force and divide it by gravity, the B here is the strength of the magnetic field. This G10 is the strength in Gauss of the magnetic field at the equator. So the magnetic field is G10 times RP cubed, which scales it to the size of the planet, so it's a measure of the magnetic field strength. So that's the G10. It's the aligned dipole. That's what is the aligned dipole. Yeah. So, and these are, you know, the mass and the gravity of the planet. That's the spin frequency of the planet.
At the beginning of your talk, you mentioned the competition between the penetration of negative charges and photoelectrons causing positive charge. Yeah. Are there estimates for how the charge states of the dust grains change? Is it fairly rapid? I mean, could something be vertically stable in one part of the orbit and then become vertically unstable as it rotates around the planet?
Yeah, it certainly can. So the largest dust grains react instantly to changes in the plasma environment. But the smaller dust grains, they take a long time to charge up or charge down. So if you had a really, really small dust grain, like a few nanometers, if it's orbiting in a different environment, it's probably just going to stay at its average the whole time. But a large dust grain, every time it actually passes into the planet's shadow, it's going to become negatively charged because there's no sunlight. And then when it comes out of the shadow, it becomes positively charged, and you get this flip-flopping in electric potential. And that drives dynamics a lot. That's something that I'm looking at now, actually. Yeah.
Okay, well, if there's no further questions, Daniel, thanks very much for your great talk. We also have a special SETI mug for collecting your dust grains in. Yeah, please join me in thanking Daniel.